Okay, so I guess we'll get started. Today we're happy to have Heidi visiting us from Ohio State University. Heidi did her PhD at Stanford and has also been a postdoc at Caltech and University of Michigan.
Yes.
And just recently started at Ohio State. Heidi has a lot of experience in large-scale structure of the universe at various scales. She's done a lot of work on zoom-in simulations of individual halos, and also has extensive experience involving the cosmic infrared background. But today she's going to be telling us about another one of her interests, which is how to probe dark energy with galaxy clusters.
Thank you so much, Simon. Good afternoon, everyone. Today I'd like to talk about probing dark energy using galaxy clusters. I will start with an introduction about dark energy and galaxy cluster surveys and growth of structure, and then I will talk about how we use galaxy cluster surveys to measure dark energy. I will then talk about my work on using simulations to better understand cluster mass calibration, focusing on the galaxies, gas, dark matter, and the clustering of galaxy clusters. About 40 years ago, Saul Perlmutter, Brian Schmidt, and Adam Rees found that the universe is accelerating. They used Type 1a supernovae to accurately determine the redshift distance relation. The Type 1a supernovae are standard candles in the sense that their peak luminosity are constant across all these systems, so they can be used to calculate distances very accurately. The redshift distance relation basically tells us the expansion rate of the universe, and they found that expansion is accelerating. This is very strange. For the gravity, as we know it, if I throw an apple into the sky, it will fall back down to the Earth. But if I manage to throw an apple very fast, faster than the escape velocity of the local group, it will start slowing down, and after it escapes the local group, it will start to run away faster and faster. That's what the acceleration of the expansion means. This means that gravity is very strange at cosmological scale. To explain this strange behavior, one of the most commonly used model is dark energy. It acts as a repulsive force on cosmological scale and causes the cosmic acceleration. And we have another strange dark component, the dark matter. It has gravitational interaction but does not emit light. But we know that we need this dark component to explain the structure we observed in the universe. Also, we need them to explain the motion of galaxies and stars in the universe. And finally, the less than 5% is what we can observe, the gas and stars in the universe. And by observing this less than 5% of the visible matter, we infer where dark matter is and how structure form. And using how structure form, we infer the property of dark energy. Dark matter and the dark energy evolve differently. Dark matter are particles, so their density dilutes as the universe expands. Here I'm plotting y-axis is density, x-axis is the scale factor, or the relative size of the universe. As the universe expands, dark matter dilutes as rho to the minus 3 is basically the volume, 1 over the volume. For dark energy, if we just assume the simplest model cosmological constant, its density is going to stay constant. And at some point, dark energy starts to dominate the energy budget of the universe. This crossover occurs about 5 billion years ago, which also marks the onset of the cosmic acceleration. But dark energy does not have to be cosmological constant. In general, we often write the pressure of dark energy is W times the density, which we call the equation of state. And if we write this way, the dark energy density will scale as a to the minus 3 times 1 plus W. And for the simplest model, W is minus 1 and which correspond to the cosmological constant. We really want to know what causes the cosmic acceleration. And as I said, one model is dark energy. But if it is not, then general relativity does not work at cosmological scale. And if it is dark energy, and we'd like to know if it's a cosmological constant. If it is not, then is it a scalar field? If it's not a scalar field, then we need more exotic ideas for dark energy. And if it turns out to be a scalar field, we'd like to know what's the equation of state. And also, it could also be just a cosmological constant with W equals -1, but we still need to find out why it is so small, much smaller than the quantum fluctuation we expect. We like to answer these questions. And it is not enough just to measure distances and redshift. We need other probes that other than the expansion rate of the universe. Dark energy has one more very important effect. That is, it slows down the growth of structure. Here I'm showing two sets of simulation. The top one has 70% of dark energy, and the bottom one has no dark energy in them. So they were set up so that they have roughly the same number of massive halos at redshift 0. So we can see that for the one with no dark energy, it has very little structure at redshift 3, and the structure grow a lot between redshift 0 and between redshift 3 and today. And for the one with dark energy, you can see that you can pretty much trace the same structure from redshift 3 to today, and structure grows slower. And we can also quantitatively look at the linear growth function as a function of time. The linear growth function basically tells us in a given area or a given volume what's the density fluctuation in that volume, and how does the density fluctuation in this given volume evolve with time. So with no dark energy, 100% matter, this growth function is a linear relation. But if we have dark energy, we can see that the growth of structure slows down at late time when dark energy dominates. So if we look at the sky and we observe these high density peaks as a function of time, we can use them to constrain how much dark energy is there in the universe, and also to constrain the equation of state of dark energy. And that's actually what we do with galaxy cluster surveys. How do we use galaxy cluster surveys to constrain dark energy? Galaxy clusters are the highest density peaks in the universe. And if we look at the optical image, it's a cluster of red and bright galaxies. And this is only 2% of the total mass in such a system. And it has about 10% hot gas, which shine in X-ray and also interact with the CMB photons. And the largest part is the dark matter halo, which is about 88% of the total mass of this system. And such a system has a mass about 10 to the 14 to 10 to the 15, and spans a few million parsecs across. Here I'm showing an embodied simulation how a galaxy cluster formed. This is an embodied simulation simulating only the gravity of a 10 to the 15 solar mass halo. You can see that we start with a small density perturbation, and this small density perturbation forms small halos, and they orbit around and merge with each other to form bigger halos. And you can see that there will be filament structures along which these subhalos move. And you can see that these small halos keep merging with each other and form 10 to the 15 solar mass halos in the end. And all these bright regions are where galaxies, or the member galaxies of the cluster will form. So we can measure the dark energy using the number counts of galaxy clusters. The basic idea is that we observe a large area in the sky, and we identify systems look like this. And then we understand our completeness and contamination. And schematically, we have cluster counts as a function of mass. In a universe with no dark energy, we expect to see higher number counts and also stronger evolution. But in a universe with dark energy, because dark energy slows down the growth of structure, we expect to see fewer clusters and also slower evolution. If we know the expansion rate of the universe, we know how the volume of the universe scale with times, so then we can use the cluster number density to constrain growth of structure. But we can also, but the cluster counts is the density multiplied by the volume. And with the volume, we also have the expansion rate. So the number counts of galaxy cluster actually includes both the expansion rate and geometrical information, or the expansion rate. And therefore, they are powerful probes of galaxy clusters. They are powerful probes of dark energy. Here I'm showing an example of dark energy constraints from galaxy clusters and other probes. The x-axis is the dark energy density, and the y-axis is the equation of state. And here we have supernovae in purple, and we have H0 plus BAO, and Planck. And this blue contour is the results from the SPT galaxy clusters. You can see that this constraint is not very tight, but it's going to change with current and upcoming surveys. So there are several ongoing dark energy experiments. One of them is the Dark Energy Survey, which is taking its last season of data, and I myself had the pleasure to go to this beautiful 4-meter Blanco telescope in Chile to take the survey data. And by the way, it's named Blanco not because it's white. It's named after the Puerto Rican astronomer Victor Blanco. And it's observing 1/8 of the sky and taking images for about 300 million galaxies. And next year, we will see the first light from the Large Synoptic Survey Telescope. And it is going to operate for a decade and imaging about half of the sky and about 1 billion galaxies. And in slightly longer term, NASA is planning the WFIRST, or Wide Field Infrared Survey Telescope. And it's a space telescope, so you will have imaging quality like the Hubble Space Telescope. It is like we will be imaging 2,000 square degrees of the sky, or 2% of the sky, with the Hubble Space Telescope image quality, which will also image about 1 billion galaxies. The financial scales of these experiments in US dollars are actually similar to the number of galaxies they observe. So the Dark Energy Survey costs about $1 billion, and LSST costs about, $100 million for DES, and LST costs about $1 billion, and WFIRST costs about $3 billion. So how do we go from the observed counts to dark energy parameters? So given a dark energy parameter, we can predict the true number counts as a function of true mass. But the true mass is not observable. We need to infer them using some methods, and then you will have some scatter and possibly also some bias. So the inferred cluster counts versus inferred mass will look like this. It deviates from the underlying true counts versus true mass. And to recover this true number counts and to recover dark energy, we really need to know this step, the mass calibration, very well. So the accurate halo mass measurements are the key for this type of measurement. To demonstrate how important the mass calibration step is, here I'm showing one figure from the Planck 2015 results. So the x-axis is the dark matter density. Y-axis is sigma 8, the density fluctuation in a sphere of 8 megaparsec per inch. So this black line is from the primordial CMB. And there are 3 results. The 3 color contours are from SZ clusters by using different mass calibration methods. So you can see that by using different calibration methods, you can go from perfectly consistent with CMB to 2 sigma tension with CMB. So it's very important that we have correct and unbiased mass calibration. So how do we measure the mass of galaxy clusters? We can, from optical, we can basically count how many galaxies are in a cluster, or we call this number of galaxy richness. Or we can take spectra of galaxies and calculate the velocity dispersion. And we can observe the hot gas component by looking at its X-ray. Its luminosity and temperature are highly correlated with halo mass. And we can observe them in millimeter wave. This hot gas interact with CMB photons and cause the so-called Sunyaev-Zeldovich effect, which will cast shadows in the CMB maps. And finally, we can observe dark matter halo using gravitational lensing. And if we have a large area of surveys, we can look at the spatial clustering of dark matter halos. I'll move on to talk about my work on using simulations for cluster mass calibration. To quantify how the observed property is related to the underlying dark matter, I developed this simulation I call Rhapsody, which stands for Resimulated Halo Population for Statistical Observable Mass Distribution Study. I myself am pretty proud of coming up with this acronym. So this is actually motivated by our initial condition generator called MUSIC, multi-scale initial condition. So I start with a 1 gigaparsec cosmological simulation. There are a lot of massive clusters in them, but they all have very low resolution. So then I zoom in on one cluster at a time and resimulate them with very high resolution so that we can really resolve those locations or subhalos where the member galaxies form. And I did 96 of these clusters, and I select them so that all of them have the same mass. But it turns out that in the simulation, they all have very different properties. And I'm quantifying the scatter of these properties. Here's the picture of all of them. So I sorted them so that the galaxies in bottom rows have more galaxies. Remember, they all have the same mass. But if we look at their galaxies, we tend to overestimate the ones in the bottom row. And I also sorted them so that they have higher concentration to the right. If we observe them using weak lensing, the higher concentration one will have stronger lensing signal. So we'll also overestimate their mass if we use weak lensing. I also studied their formation history in detail. Here are the formation history for 4 different halos. And especially this one is particularly interesting. It has lots of mergers at redshift 3 and has already have lots of its mass in place at redshift 1. But somehow it just stopped evolving and does not gain much mass between redshift 1 and 0. And this one is completely opposite. It has very little thing going on at redshift 3, but suddenly have lots of mergers at redshift 1, and then achieve the same mass as other halos. You can see visually that halos formed in these 2 different ways look quite different. There are a lot of subhalos around this one that formed pretty late, and this one that formed early looks pretty smooth and without fewer substructures. I also collaborate with people work on the hydrodynamical simulation for these clusters, and we call them Rhapsody in G. And there are 10 clusters selected from the n-body sets, and we run the adaptive mesh refinement called Ramses to generate a simulation. It has slightly higher mass resolution, slightly bigger dark matter particles because it's more computationally expensive. And we set the star formation efficiency to be 3%. And we put AGN thermal feedback models. We inject the density to 2 times the cell size. It's a modification of the Booth and Shea prescription, so that we can actually match the observed stellar mass, halo mass relation from observation. So below, using this set of simulations, I will discuss how we measure cluster mass using velocity dispersion, X-ray gravitational lensing, and clustering. Let's first focus on the velocity dispersion. The idea of this actually dates back to the 1930s from Fritz Zwicky. He observed that he measured the velocities of galaxies in the coma cluster. He found that the velocity dispersion of these galaxies are so high that such a structure cannot possibly be held together by the visible matter themselves. So there must be some invisible matter that is holding this structure together. That is the earliest evidence of dark matter. But now we can use the same idea to do precision measurements for the halo mass. The basic idea is the Virial Theorem that the kinetic energy is proportional to potential energy. Kinetic energy is V squared, and potential energy is Gm over R, which is proportional to m to the 2/3. And observationally, this V squared is, we can measure this V squared by the velocity dispersion of this system. Here I'm showing the velocity dispersion of the simulated galaxies. So the y-axis is velocity dispersion. The x-axis is the halo mass. And the gray bands are from dark matter particles. And this relation agrees with previous embodied simulations, which is not surprising. But the new things I found using this simulation is that the velocity dispersion of galaxies actually depends on how we select them. For example, the red line here corresponds to that we select only 10 galaxies per cluster. Measuring the velocity dispersion requires taking spectra for galaxies, which is expensive, and we try to do them with as few galaxies as possible. But this is showing that if we only take the spectra of 10 brightest galaxies, and then we tend to underestimate its velocity dispersion, and which leads to about 10% mass bias. Why is this? This is because galaxies don't behave like test particles. We know galaxies have sizes, and when they pass through dark matter density field, they feel dynamic friction, and then they can be tidally disrupted. So to quantify their deviation from test particles, we use the so-called velocity bias, which is the ratio of the velocity dispersion of galaxies divided by the velocity dispersions of dark matter. Dark matters are test particles. And here is the velocity bias. The x-axis is the number of bright galaxies we use. So here corresponds to that we use only very few of the brightest galaxies. You can see that the velocity bias is less than 1, means that these bright big galaxies or subhalos, they are slower than the velocity of dark matter. This makes sense because these are big subhalos. They pass through the dark matter density field, and then they are slowed down by dynamical friction. But the interesting thing is that if we start to select lots of smaller subhalos, we start to pick up a fast velocity dispersion higher than 1, faster population. So for these, we are looking at small subhalos. If they pass through the dark matter density field too slow, and they tend to get tidally disrupted. And the one we can observe are the ones that are not disrupted, which means they are the faster population. So this effect needs to be taken into account when we select galaxies to calibrate their mass. So I'd like to move on to the second component, the X-ray, the hot gas. So for hot gas, again, we use the Virial Theorem that the potential energy is proportional to kinetic energy, which is now Kb times T. If we plug in the mass and radius of cluster, we get 10 to the 7 Kelvin. That's why the galaxy clusters shine in X-ray. The luminosity is proportional to the electron density square, and the gas density is proportional to the electron density. So we can use the X-ray luminosity to infer the gas mass of clusters. The gas mass is tightly correlated with the total mass of the cluster. Here I'm showing you not a result from simulations, gas mass versus total mass. We see a pretty tight relation, and with a scatter about 8%, which agrees with previous simulation. The new thing I found is that if we combine the stellar mass from such a system, so as I said, that gas mass comes from X-ray, and we can also observe stellar mass from optical. Then the sum of the gas mass and stellar mass versus the total mass have a smaller scatter, about 4.7%. This is almost a 2 times smaller scatter. Why is a smaller scatter a good thing? So in the absence of systematic errors, 2 times smaller scatter actually means that the statistical power is improved by 4 times. So this is saying that for a given X-ray sample, if we manage to get stellar mass, we can more effectively reduce in the scatter and improve the statistical power of the same sample. And the reason why there exists such a tighter scatter is that I found that the stellar mass and the gas mass are actually correlated with each other. So here the y-axis is gas mass, x-axis is the stellar mass, and they are fraction, and they are all divided by the universal value taken from the simulation. So the gray bands here are from my simulation, and the the two sets of data points are from observations. You can see that we can sort of see this anti-correlation in observations, but again, that the error bars of observation is still pretty big. So if we can improve the stellar mass measurement, and then we will also be able, at the same time, we will be able to improve the statistical power for like X-ray surveys. To move on to talk about gravitational lensing from clusters. Gravity bends light. Here is an observer observing a faraway source galaxy. And here's a dark matter halo acts as a gravitational lens. So the light from this source galaxy will be bent and distorted, so the observer will observe a lensed galaxy image. Here is an example. So the dark matter halo of this red galaxy serves as the lens, and the background galaxy is distorted into a ring that is the so-called Einstein ring. This kind of strong lensing is pretty rare. It requires almost perfect alignment between the source, the lens, and the observer. And a more prevalent and more important effect is the weak lensing effect. It's everywhere. It occurs whenever there is density contrast. Here I'm showing an image of galaxy cluster. Near the center, you can still see this giant arcs, a strong lensing effect. But if you look at the outer region, you can sort of see that the galaxies tend to align tangentially, and that's the weak lensing effect. So as I said, that the weak lensing effect is very subtle. So unless we have used Subaru telescope, unless we can use Subaru telescope to stare at it for a long time, it's hard to detect them. But one thing we can do with imaging survey is we can combine the weak lensing signal for multiple clusters to improve the signal. For example, in this cartoon picture, we combine all halos with 3 galaxies in them. And so one way to select how we stack clusters is to use richness, basically the number of galaxies in a cluster. For example, here I have, in simulation, I have halo and their halo mass and their richness, and have a big scatter, about 40%. And since halo is not observable, we can only select on richness. For example, here I select richness 30 to 40 or 40 to 80. And I color code them by blue and green. And then I can measure their weak lensing signal. For example, like this, the lensing signal is proportional to the projected mass density. And the different richness, the halos of different richness will have different amplitude of the weak lensing signal. And by using this lensing signal, we can constrain the mass and to constrain the richness mass relation. So far, almost all weak lensing analyses assume halos are spherical, or they assume that the stacked halos average to be spherical. But we know that dark matter halos are not spherical. They are triaxial. For example, if a dark matter halo looks like an olive, and if its long axis is aligned along the line of sight, so its total mass will be projected in a smaller area. So we tend to see a higher lensing signal, because lensing signal is sensitive to the projected density. And if the long axis is parallel to line of sight, the same amount of mass is projected to a larger area, and then we tend to see a lower lensing signal. So this is exactly what I found in simulation. So here I'm plotting the lensing signal, again, a projected density profile. as a function of projected distance. And then the red curve here corresponds to this kind of configuration. And we can see an excess in the lensing signal. And then the blue and the purple curve correspond to this perpendicular configuration, and we see less strong signal. And the interesting thing is that not only in small scale this matters, this orientation also affects the signal at about 20 megaparsec, which is well outside the radius of galaxy clusters, which means that even at 20 megaparsec or larger, there are still correlated structure affected by the orientation of these halos. So this effect wouldn't matter if the red and blue cancel each other perfectly. But what we find is that they do not cancel each other because there's a selection effect of our clusters. So to quantify the orientation, the angle I is the line of sight. It's the angle between line of sight and the long axis. So this one is I equals 0, cosine equals 1. And this configuration is I equals 90 or cosine equals 0. So I go to a simulation and then apply cluster finding algorithm on it and see what I recover. Here is just a histogram of these cosine angles. If I look at the halos, all of them, then I get this pink distribution, which is uniform, which means that there's no preferred direction in our simulation box. But if we apply the cluster finding algorithm, or the red mapper algorithm, we get an excess of this kind of aligned halos. So this cluster finding algorithm preferentially select halos that are aligned like this. So it is easy to understand because we are looking for high density of red galaxies. And if they are aligned like this, then you tend to see a higher density of red galaxies in a smaller region. And these clusters are more easily identified. While if those galaxies are spread across a larger area, and then they can be easily missed. So that's why we see there's just some clusters that are missing. And this selection effect also affects the richness. So here I'm plotting the cluster richness as a function of halo measured in simulation. And this red curve corresponds to this configuration, and blue corresponds to this configuration. We can see that the parallel configuration tend to have their richness overestimated because of the effect I said that smaller clusters are concentrated, smaller red galaxies are concentrated in a smaller area. And which is a non-negligible effect for DES, and I'm working on incorporating this effect into the DES cosmologic survey, cosmologic constraints. As I said, that weak lensing is a subtle effect, and we need better telescope to observe it. And the WFIRST, the NASA satellite WFIRST will achieve unprecedented accuracy in weak lensing. And I'm working on the forecast and theory for the weak lensing that's needed for WFIRST. For example, in this calculation, I show that the fractional accuracy of mass as a function of redshift for clusters of different mass. At about 0.3 redshift, we can achieve about better than 1% mass accuracy for the mass, for the 10 to the 14 solar mass halos. And even for redshift 1, which have not been observed before, we will still be able to calibrate the cluster mass to about 2%. And of course, this calibration, these constraints will change depending on the systematics it's involved in the survey. And also, these mass constraints are directly translated to the constraints on the growth of structure. Here I'm showing the fractional accuracy of sigma 8 as a function of redshift. Here, I assume that the sigma 8 at different redshifts are independent of each other, which means that the sigma 8, which is sigma 8 of z, is a measure for the growth of structure. And these are from different mass calibration methods. For example, the orange one corresponds to a 1% mass calibration, which can give us about 2 to 3% of sigma 8 constraints across all redshifts. Finally, I'll talk about one last method from using the clustering of clusters to measure the mass of dark matter halo. We know that the dark matter halos are not distributed randomly in the sky. They have some clustering. Here I'm showing two sets of simulation. These are the distribution of high mass halos, and these are the distributions of low mass halos. So low mass halos, they not only have higher density, but they also are more uniform. More massive halos are more clustered in space. And schematically, we can quantify this using a so-called correlation function, which is basically the number of pairs as a function of distance. Of course, we need to take out the impact of volume, so we divide it we compare it with respect to a random distribution. So if a set of points are randomly distributed in the sky, it will be a flat correlation function. Dark matters are not randomly distributed, so it scales almost like a power law. And for low mass halos, it will be proportional to dark matter, but has higher amplitude. And the higher mass halos will have even higher amplitudes. So to measure this from a survey, we select clusters based on richness, because this is one of the easy but crude way that we can estimate their mass. So we can bend them according to their richness, and using clustering to get the halo mass, using a correlation function to get the halo mass. And this is the correlation function that from those two bins, and then these different amplitudes can help us constrain the mass for clusters. And this just recently become possible with the DES 5,000 square degree of data, because this kind of experiment requires a large area, a large sample. One of the important systematics in this type of experiment is the projection effect. In DES, we only have images of galaxies. We do not have spectroscopy for them. So for example, if here are 4 halos, one has richness 7, one has 2, and 3, and 4. So if we look at them, we don't know their distance, then we can mistaken all of this to be one halo with 13 galaxies in them. So this is going to affect our clustering measurement. And this is the correlation function without projection, meaning that we know the position of every halos. This is again in simulation. And with projection, we will see that the correlation function are altered. There are 3 effects. One is that it washes out the small scale clustering. For example, in the previous cartoon picture, there are 4 halos, 6 pairs. But if we just project them to be 1, then we don't see those 6 pairs, we just see 1 halo. So that's why we see a dip in the small scale. And also, we are boosting the richness of clusters. Just as I say in that cartoon picture, the cluster has richness 6, but then we mistaken it to be 13. And finally, it's biasing the selection towards a more clustered halo, because in a region, if a halo lives in a more crowded area, we tend to see a stronger projection effect and then get a biased high clustering amplitude.
questions?
Oh, some.
Okay. So to summarize, at the beginning, I talked about that we need to understand the cosmic acceleration, we need to measure both the expansion rate and growth of structure. And the galaxy cluster provides an opportunity to do both. And the abundance of galaxy clusters is particularly sensitive to growth of structure, and we use simulations to help us understand cluster mass measurements. And I presented the method using galaxy dynamics, and I found that the bright galaxies tend to be slow. And I presented simulations for X-ray, and I found and talk about that we can combine gas mass and stellar mass to reduce the uncertainties. I talk about lensing and the orientation of halos matter for stack analysis, both for the weak lensing and the richness estimation. And the clustering is recently possible with the 5,000 square degree data from DES. And upcoming missions like WFIRST will achieve unprecedented precision for gravitational lensing for clusters and pushing our horizon further to constrain the growth of structure at higher redshift. Thank you.
All right. Do we have any questions for Heidi? Yeah. Can you go back to the slide where you had the effectively alignment on the lensing?
Yes. This one.
Yeah. Is there a reason why the effect seems to be minimized at a couple megaparsecs? The red curve comes down and the blue and purple ones come up?
This is around the virial radius of the halo. And
So stuff around the virial radius was the least biased by.
right. It actually makes me think whether we can actually use this scale to actually try to mitigate such effect. Yeah.
Yeah.
So you had a slide where you said, showed the different merger histories.
Yeah.
And I'm wondering, you go back and sort of look at the impact of, say, recent major mergers or something like that on various things you looked at, like certainly the virial estimate of the mass, and also certainly the X-ray and SZ signal is going to be enhanced during a major merger. Maybe sort of examine
So
those effects.
I look at some of them, and one of the strongest is actually the concentration measurements, and then the late form or the recent form one will be less concentrated, and the one that does not have much major merger have higher concentration, and then their lensing will be higher, and same for X-ray. And of course, it would be very interesting to look at multi-wavelength observation, see if they consistently show different properties, biased properties across the spectrum. Yeah.
So
Yeah.
You've got them sort of current morphology, sort of, okay, this is a merger, therefore I'm going to be biased. one way or the other.
Yeah,
Various signals.
right. And to connect to observation, it's actually the biggest problem is that if it's a merger, then we don't know how to define the center. Yeah, so that's also the tricky part with dealing with mergers.
Yeah.
So in your simulations, when you measure the gas mass and the star mass, that's mass within the virial radius?
Yes.
Okay. What is that centered on?
Yeah, so
I think it's a spherical delivery, assuming?
yeah, so in simulations, we have the luxury to look at the highest density, like the density peak in the simulation for dark matter particles. Basically, in a dark matter halo, we can measure local density in every point, and then we find the highest.
Okay, so you use just the dark matter particle?
Yes, to define the center.
And then you just take a sphere around it?
Yes.
So I was wondering on the last thing that you showed, when
Yeah.
you had the impact of projection on
Yeah.
the mass from clustering,
Mm-hmm.
is there any information, is there some like photometric redshifts in here? Is there any redshift information here for these objects?
There are
Or is it the
photo.
whole bin from
Yeah, there are photo Z's.
other?
And again, the problem is that when you run the halo finder, you just mistaken all these 4 into 1. And then this range are well within the photo Z error, so you can't tell them apart. So yeah, so you count them as 1. Especially if it's a high density region. They are already more biased, but then you just group all these different halos together and count them together.
Right.
Yeah.
They have many close to each other.
Yeah.
Okay. Yeah, one last question?
Sure. So back to the measuring the virial mass. How did you select the galaxies? And I'm
So,
sort of wondering,
yeah.
maybe if you selected the galaxies using some, like concentration rather than brightness or something like that.
You mean in simulation or in observation?
Well, how do you calibrate or determine the mass bias?
Right.
Maybe you could say something. Well, if I selected a
Yeah. So in my simulation, I just assume that we start from the biggest subhalo, the one with highest V peak. Yeah, the highest mass in its formation history. And we assume it corresponds to the brightest galaxy. But in observation, it will be a lot more complicated. They might not be red, or you might get some projection from other galaxies. Yeah. Yeah, it's going to be a lot of fun to look into.